matchboxes or?
I don't know. Con systems is really just taking the building blocks here and putting them together into a system of large elements, and specifically aligned with analog communication. Okay, we're back live. So, continue our last two classes. This is the last class of the semester, and we were talking about different forms of these transfer functions. And so we have the rational form of polynomials, and if we factor those, we get a cascade form that describe exactly the same transfer function. So one we might consider a vector of the coefficients of the polynomials, and the other we might consider vectors of the zeros and the poles. Here's a rough view of one stage of this transfer function with one zero and one zero and one pole, and then you just repeat this again and again, however you want. The zeros and the poles fully describe the filter. And that's one thing that I want to get across to you. And so one thing that's often done, and we'll do an example of this here in just a little bit, is you draw a complex plane, the imaginary part and the real part of z's, and you put on this where your zeros are and where your poles are. And over time, by doing this, you get very good at figuring out exactly where your just looking at this diagram, you understand whether your filter is stable or not, whether it's a low-pass filter, whether it's a high-pass filter, where the resonance is, and then even beyond that, you often start to think schematically and diagrammatically of saying, well, I'm going to build a filter. I want some poles over here. I want some zeros over here, and then that becomes your way of thinking about the synthesis or the design problem. Okay, none of these are better than the other. It's just how they're just different tricks and different things you do. So as you work more and more and more with DSP and use all these tools, that familiarity kind of comes into play, and you end up using it in your toolbox. Okay, for now we just we'll just slug them out, but eventually there becomes some reason to the madness, I guess. All right, so let's do one more example, and where are we? There we go, and I'll just label this as 11. And the transfer function h of z now I'm going to actually come back to this example in a completely different way in a little bit, but this is sort of the sterile approach, mathematical approach to this particular problem, and we've seen this a bunch of times. I'll say that a is greater than 0, and so therefore this is going to be a to the n for n greater than 0, and it's going to be 0 for n less than 0. So just to remind you of a concept we've had, this is a causal system. This will be a causal system. What am I doing? Hang on. Let me start all over. I'm getting ahead of myself, okay? My h of n, I don't want to go yet into the Z-Transform just yet. This will be a to the n u of n, and this will be for a greater than 0. And so this will equal a to the n for n greater than 0, and it'll be 0 for n less than 0. And so now I can say with a straight face that we know that this is causal, because the transfer function is, the response to a delta function does not happen before the delta function does. Okay? Most physical systems are causal. Okay? In the magic world of DSP, you can play games with your time faces and actually do work with it's not causal. It's a little tricky, but you can turn an unstable system into a stable system by making it non-causal. So that's in fact, I don't know if you worked with, I don't know if you've ever had a class from Bob Hunt, or if you know who he is. He's a professor emeritus. He's spending most of his time starting a company on power electronics company. But he also did, early in his career, he did the flight stability algorithm for controlled flight of unmanned vehicles out of NASA, out of Goddard. Out of JPL, Jet Propulsion Lab. And one of the things was to turn an unstable system into a stable system by flipping around and doing the DSP that way. Very, very elegant, very clever solution that he did. All right, so here's my transfer function. It's very, very general. It's not unlike a Fibonacci sequence, right? If you think about this exponential decay, depending on whether this is going higher or going lower. So in some senses, we're actually revisiting a problem, and in a little bit we'll look at it even more physically. So if I Z-transform this, my delays are represented by the z to the minus n. And so I can rewrite this a z to the minus 1 all to the nth power. Okay? And there was those pesky little summation formulas that have popped up continuously in this course. You probably half knew them coming in, and probably every time you see it, you go, oh yeah, right? So these come up a lot. And what I'm getting at here is this is one of those little tools that you might, I don't, maybe memorize if you're so inclined, or at least remember that they exist. Anyway, if you do the summation formula, then it's 1 over 1 minus a to the z minus 1. And if I factor this, I get a z minus a. So if I want to, I can say that there is one pole at z equals a, and I can say there's 1, 0 at z equals 0. And so now we'll go and we'll try our pole 0 plot. The imaginary part of z and the real part of z. And so if I plot the 0, the trivial 0, I put a circle at the origin. That's the notation for, you can yell, you don't have to like hint. You can throw something at me when you can't see the paper. So here's the location of my 0. And if a is real, then my pole will be sitting out here on the real axis at location a. So just notice that on a pole 0 plot, zeros are represented by a 0 or a circle, and on a pole 0 plot, the resonance or the singularity is represented by an x. Okay, and so this is one of the simplest pole 0 plots you can imagine. Okay, but that's our starting point. That's our first building block. Now let's just take a quick look at some of the cases here. I'm going to draw a unit circle. This is for the magnitude of z equal to 1. So here's 1. Here is imaginary I times 1. here's minus 1, and here's minus I times 1. And so if I as long as I move here, my radius is always going to equal to 1. And so this is refer to that as a unit circle. Remember, there's a 0 at the origin. I won't mess with that too much. If my pole sits somewhere inside my unit circle, that means it's less than 1. That means this guy here will decay. Okay, if it's between 0 and 1, like a half, that means that this summation will converge. Okay, so I can draw that looking something like that. If my pole is negative and within the unit circle, if it's real and negative and it's within the unit circle, then that would be an example of minus 1/2. When the n is even, the minus sign cancels out. When the n is odd, I have leftover minus sign. So I get the same behavior, but I get an oscillation. So I get a nice converging system, but one is only positive and the other is oscillating. Okay. I think we talked about these cases before, but we just probably didn't. It's not bad to remind ourselves. Let's. Here's our unit circle, and let's move our pole right onto the unit circle. Okay? Positive and right on the unit circle. That means that this A is 1. So whatever I raise 1 to any power, 1 to the 17th is 1. And what that means is this guy is going closer and closer to the unit circle. These takes longer and longer and longer to converge. And when they hit the unit circle, out pops a stream, an infinite stream of 1s. Perfect accumulator turns a delta function into a step function. Okay? Also, well, I'll get there in a sec. Okay? So again, we're thinking in terms of sliding this pole closer and closer and closer to the unit circle. Let's go the other way. Let's take this guy and slide it right onto that, to the -1 number. And -1 to any even power is going to be 1. -1 to any odd power is going to be -1. So this behavior grows each one of these, but it doesn't change the oscillation part of it. So I just have plus and minus 1s on my output. Okay? So again, just thinking about one silly little pole, moving it around, changes drastically the impulse response. Okay? Let's do 2 more cases. Let's cross over the unit circle. So now my A is greater than, you have to yell. So now you cross over the unit circle. So A is greater than 1, like it's 2. And all of a sudden, I don't have a decaying exponential anymore. I have a rising exponential. If I cross the unit circle in the negative direction, I still have that rising exponential, but now the odd and even power of n flips the sign back and forth. So I have a diverging oscillating series. Okay, so pole position matters, and one huge part of this is pole position relative to the unit circle matters, because this is clearly, these systems are clearly nice and stable, and the pole is nestled inside that unit circle. If this step function behavior, the pole is right on the unit circle, and these are marginally stable. These are marginally stable systems. Okay? And then when you cross the unit circle, you go unstable. Okay? So in general, whenever you see a pole, you look and you say, where is it relative to the unit circle? And that gives you a measure of stability or instability of your system. Okay? Right-hand poles versus left-hand poles give you a sense of whether things are oscillating. Okay? And I also want to point out one more thing, which is, you see this form of our transfer function. This is an infinite impulse response. Infinite impulse response. One delta function leads to an infinite number of delta functions. And that's exactly what we see in each one of these cases. This guy will never quite, it'll converge to zero, but it will never quite get to zero. Okay? So in all these cases, one delta function in gives me an infinite stream of output functions, and that's another reinforcement about what we mean by an IIR filter. All right. Now, so we've seen the direct form realization, which is the polynomials and the polynomials. We've now seen the cascade realization, which is products of the pole zero, the factored one. Okay? There's another realization, and it's the parallel realization. And so this starts with a product of poles and a product of zeros. And it switches C minus, let me write that as a P sub K, and this is a 0 sub K. Won't worry too much about the zeros for now. Z minus PK plus B Z minus P P1, P2, and so on and so forth. Okay? So what we do is we can take this and we can expand this out into this. I don't know if have you played with these kinds of transformations, spacing on what it's called. Anyway, so let me do an example of how this works. So we instead of a product here, we now have sums, and the denominator of each of the sum is one of the zeros, one of the poles. Okay, so let me just do an example to teach this. H of Z So I'm just making up a transfer function, okay, which we now can do, right? What this says is I want a pole at a certain position here, a pole at a position here, and I want 3 zeros sitting up on top like that. Okay? So I'll write this more in cascade form. So I have z minus 1 cubed. So my zeros are right on the unit circle. And then I'll have a z. So they'll have a 0. I'll have a pole at the origin. And then I'll have a z minus 1/2. So I'll have a pole at 1/2. And I'll have a z minus 1/8. So I'll have a pole at 1/8. 1/8. So far it looks like a stable system. Okay? And I will express this as a z times an a over z squared. So that's my 1 over z term. Plus a b over z. That's a constant offset. And then one term for each of these poles, z minus 1/2 and d of z minus 1/8. And so now you can see that if instead of building this as a feedback loops with the direct form 1, instead of realizing this as a cascade, I realize this is a parallel connection of a 1 over z squared, a 1 over z, a 1 over a feedback loop here, and a feedback loop here. So 4 parallel structures, 4 structures in parallel will do exactly the same as the other 2. So it's the parallel realization. Okay? So, I've actually woken up a little bit, and I'm remembering that this is a partial fractions. Have you guys seen this partial fraction stuff before? Good. I never know what's in our curriculums. So I guess, do you want me to go out in some detail on this, or I might as well. So the way, just to remind you, the way once you set this up. Once you set up the way you want the form of it, you have to find A, B, C, and D. And you do that by multiplying through this is z minus 1 cubed. Multiply through this guy across all these, and you have an A z squared minus 5/8 az plus a over 16 plus b z cubed minus 5/8 b z squared plus b over 16 z plus c z cubed minus c 1/8 z squared plus d z cubed minus d 1/8 z squared. Okay? And the way you solve this is you set up, you find all the terms in z cubed. You find all the terms in z squared. You find all the terms in z, and all the terms in z to the 0. Okay? So the z cubed terms, 1 is equal to b plus c plus d. 1 is equal to b plus c plus d. Where am I? 1 is equal to b plus c plus d. Is that term, is a z squared term. Minus 3 is equal to a minus 5/8 b minus 1/8 c minus 1/2 d z to the 1. Positive 3 is equal to minus 5/8 a plus 1/16 b. And the z to the 0 term is minus 1 is equal to a over 16. So this gives you a is equal to 16. Plugging into here gives you b is equal to minus 112. Plugging into these guys here gives you c is equal to minus 4/3 is what I get, and d is equal to 343 over 3. And then you've done your design, if you prefer to realize in a parallel form. Okay? And I'm glad you've seen the mathematics of that. All right. Now, 11:15, right, is when we go to. Good. I'm going to do one more example. I'm actually going to revisit the last example in the Fibonacci sequence, but I'm going to recast it absolutely completely differently. So this is my last example. And I don't want to scare you. I'll call it an example from electromagnetics. Don't hate me. You may or may not even see this in an electromagnetics course. I think about half of the class has taken EMAG, and the other half has not. I think that's the general. When I polled the class, they were either in EMAG or taking it next semester. But regardless, you won't even really see this. So let's just think a little physically. The example that I'd like you have, I think, worked in the laboratories upstairs, and so you've worked with the function generators, and you've worked with the oscilloscopes, and you've worked with, in particular, the cables, the coaxial cables that connect the two, right? So what I want you to kind of think about for a second is, lambda nu is equal to, or lambda f is equal to the speed of light. And speed of light c is 3 times 10 to the 8 meters per second. It's just a touch slower in those coax cables. The signal moves down those coax cables at about 2/3 the speed of light. But I like the gigahertz because it intuitively we think in terms of a foot, a nanosecond, and at a gigahertz. Okay? Now think about this. A gigahertz is not that tremendously fast a frequency these days, right? I mean, your cell phones work at your computers work at a gigahertz nearly. Your cell phone radiates at a gigahertz or 2. So a gigahertz is a very, very common kind of a frequency range for electrical engineers today. And 3 feet of a transmission line means that the wavelength is smaller than that coax cable at a gigahertz. So if in other words, if I send a 1 nanosecond pulse into a 3-foot long cable, I'm not loading up the entire transmission line. Okay? So let me model this. And here's my transmission line. Okay? Here's my transmission line, very, very abstracted. And I'm going to launch a V in to my transmission line. So this is my signal generator. And I'm going to set this equal to a sine wave. And so I'm load this up. And what we do in the lab, and eventually you'll realize how nice this is, but we take pains to make sure that the impedance between the signal generator and the transmission line and the oscilloscope, we make sure that those are friendly. Okay? So if we're working at very high frequencies, we have 50 ohms, 50 ohms, and 50 ohms, and that's a really nice impedance match. The world isn't always that way, right? There are 75 ohm cables out there. There are other wires on your circuit board that don't have that impedance. And what will happen is if you don't match your impedances at either end of your transmission line, you'll get a reflected wave right back at you. So even though you want all your voltage to be transmitted into your circuit or into your oscilloscope, if you don't properly terminate the ends of your transmission line, or if you use the wrong transmission line, you're going to get reflections. And sometimes this reflections can ruin your day or ruin your $50,000 network analyzer. So that's a big deal. Okay. So this is so the voltage in, voltage reflected, voltage transmitted into this particular system. There's another that's one model of this. Another one, oddly enough, is that pane of glass right behind us on the doors, and so it's a little imprecise, but there's a reflection off of the first surface of the glass. Okay, you can see yourself in a pane of glass, right? And then on the other side, there's another index mismatch, and there's another reflection off of that. And so what happens is if I shine light into this structure, I'm going to have a reflection, transmission, reflection, transmission, reflection, transmission, right? So all these, so my output VT is going to be the sum of all of these outputs, all of these time-delayed outputs, phase-delayed outputs, delayed outputs, right? Because the light goes in, it takes some time to go through the glass, bounces off the other surface, it takes some time to go back, bounces off, and so there's a delay line here, there's a delay line here, and the outputs of all of those are I sum those up with the proper delays and the proper weights, and I have a composite output. Right? So this device, this block of glass is a linear time-invariant system. The color of the light going through the glass isn't changing, so the frequency's constant stays the same, and time-invariant, that piece of glass, I've been staring at it for 22 years, and it hasn't changed. It's pretty time-invariant, you know. So if you want to think in terms of our linear time-invariant systems out there, well, that's a pretty darn good one, right? Anyway, so clearly this is a linear time-invariant system. Remember what I said is what a filter does is it splits your signals, weights them, and delays them, and puts them back together. Well, that's exactly what's going on here, right? It's splitting your signal, it's delaying your signal, it weights your signal by those coefficients, and so this block of glass is a filter structure, or the transmission line with improper terminations is a filter. Okay? So this is an example from electromagnetics, but it's also one that is very easy to think about, and in fact it fits beautifully into our Z-Transform lectures, and I'll show you. That's what I'd like to illustrate. So I'll confuse you just a little bit more. The input voltage is some amount V out. Okay. If it's a transmission line, I'll talk about a voltage. If it's a beam of light going through a block of glass, I'll talk about an electric field, which I think you've seen at least in physics. And electric field, I'll just remind you, is volts per meter. So volts versus volts per meter. Hey, we're all friends. It's 6 of one, half dozen of the other. Okay, sort of. And in a transmission line, and in a block of glass, we actually have to think about not just what's happening in time, but also what's happening in space. So what is the voltage as I move along the z-axis of the transmission line? And then if I sit at a particular point of z on the transmission line, what's happening with respect to time? So there's actually a little bit more complicated behavior of these signals in these problems because I have to worry about an e to the ikz and an e to the minus I omega t. So this signal is actually sinusoidal in space as well as time. Okay? Now, we know this as 2 pi times the frequency. This k we know as 2 pi divided by lambda. And lambda f is equal to the speed of light. Okay? So the lambda is the lambda of the waves. So if I draw this in z, the wave repeats from peak to peak at a wavelength. Okay? And really, I'm talking high school physics, right? I think that's a picture you saw in high school physics, and so I'm just kind of reminding you of that. So you know a lot of EMAG already, even if you haven't taken EMAG. Anyway, but let's just pause and take a quick note here and put this in the context of our entire semester. Okay? Most of the semester has all been about moving between time and frequency, right? Time measured in seconds to radians per seconds. Okay, so think about that. If this is a transcendental function, I need these guys to cancel out. So time, seconds, 1 over seconds, throw in some 2 pi's in there just for fun, and I have a reciprocal variable. So the Fourier transform of t gives you is omega. The Fourier transform of omega space gets you back to t space. Okay? Look at this term. Exactly the same arguments, but now instead of time, I'm going to talk about space, position. And instead of k, instead of omega, I'm going to talk about 1 over position or 1 over length. Right? And the length happens to be the lambda. So conjugate variables, time versus frequency. Time and frequency are not the only examples of conjugate variables. Okay? So there's actually a whole slew of conjugate variables out there, and all the Fourier transforming techniques work in other pairs of conjugate variables as well. Okay? So you can do Fourier transforms in z space and k space. You can do Fourier transforms in t space and omega space. You can also do it in z space and k space. The physical meaning of k space is actually momentum. So space and momentum are conjugate variables. You have to throw in some numbers like h to get the units to work out right. Okay? If you've taken solid state devices, and you think, and maybe you've seen Brillouin zones, modeling your crystal lattice in K space. Have you seen that in the valence diagrams and the conduction diagrams are often drawn? If you think about the axes there, I think that those are in K space, right? You probably can visualize this, and you probably are not remembering exactly what that axis is. But if I remember right, it's K space. And here's the trick on that, right? So again, I'm digressing a little bit, but I think it's important. In a crystal lattice, okay, like a silicon lattice, you go from nucleus to nucleus, atom to atom to atom to atom to atom. Okay? So what happens as the electrons cruise through the atoms is they're being sucked in and then repelled by atom to atom to atom. And so their speed is like being on a roller coaster. It's slow, it goes fast, it's slow, it goes fast as it trades off momentum. And it trades off momentum for potential energy to kinetic energy. So it's silly to model the conduction band and the valence band and plot it in Z space, because it repeats perfectly for 10 to the 22nd atoms. So that's silly. So what you do is you instead of drawing your sinusoid in time, you draw what's happening in frequency. But instead of drawing your crystal lattice in Z, you plot it in k space or momentum space, the movement of the electrons as it moves to and from the silicon atoms. Okay? So you've seen a little bit of this, but now you can kind of go back and revisit and say, oh, okay, that's the convenience, and that was what's going on. So by suffering through all of our Fourier transforms in the time domain, in one fell swoop, I can now show you that it applies to a dozen more problems, a dozen more conjugate variable space problems. So really, really, really powerful expansion of all the things that we've done so far. Okay, now, the delay, I need to start doing my transformation from into Z space. My delay is going to be delta, and that's like L over C, the speed of light. So meters divided by meters per second, 1 foot a nanosecond. So for whatever L is, however number of 3 feet, my delay is going to be 3 nanoseconds. A little bit longer because it moves a little bit slower through that polystyrene white material that's inside the coax cable. A little bit slower, but nothing to really going to stress us out at this point. All right, so let's write down this v of t. Okay. And I want to write down this term, and all the other terms in an infinite sum. And as you can imagine, I'm going to use that infinite sum formula. TL, TR, V input, e to the minus I del. That's my very first term through my structure. So I have a transmission on the left side, I have a transmission on the right side. The V in goes straight through, modified by these two weights, and it's delayed by exactly 1 L over C, e to the I del over C. Okay? Now I'm going to be a little bit sloppy here. I think this should be 3 I delta there. So my next term is delayed by 2 twice. By another, this delay plus this delay and this delay. So e to the 3 I delta. And then I have the 2 transmissions. And then I have the rattling off of the right mirror and the rattling off of the left mirror. And my third term is plus let's see. I need the TLs. I need the RRL twice. And I need the TR. And then I need the V initial. And then I need an e to the minus I 5 delta. And so on. Okay. So I'll rewrite this a little bit. TL, TR, VI, e to the minus I delta, times 1 plus RRRL, e to the minus 2 I delta, plus RRRL squared, e to the minus 4 I delta, and this guy gets the same, and this is, I can write as 1 plus x squared plus x cubed, and so on. These r's here are less than 1 because they're just reflections off the block of glass. And so this goes to 1 over 1 minus x. Right? That's my summation formula that keeps popping up inconveniently throughout the entire course. Okay? So if I clean this up a little bit, I get V out, or V transmitted, I should say, as TLTR, V input, e to the minus I delta over 1 minus RL RR e to the minus 2I delta. And the essence of this transfer function is exactly this delay. Recognize our poles, recognize our zeros. It's a first order, starts to look very familiar to the other example that we had earlier on. If I write this in terms of my powers, clean up I left out a few steps, but I cleaned up notation a lot. So this is just the power, the ratio of the power, so the complex, the real part squared plus the imaginary part squared. And I noticed that this is a resonance denominator. So whenever delta is equal to -1, then the denominator gets big. Okay? When delta is equal to 0, I have unity response. When delta is equal to, what is it, pi? If you flip sine, pi over 2, minus pi over 2, flip sine, and that guy almost, if we could figure out a way to make that equal to 1, you'd have an infinite. Okay? So if I plot this, I have a set of peaks, and this peak is in terms of delta. Thank you. And I have peaks. These peaks are in delta whenever k is equal to L pi over capital L, and that's an integer. So whenever I have an integer number of pi over L, or another way to say that is when the delay is an integer number of wavelengths. So again, all these waves, what comes through the device is all these waves, sinusoids. The sinusoids are rescaled because of R's and T's, and then they're shifted over in phase. So whenever they add constructively versus destructively, I'll get nothing out if they cancel. If all the reflection terms cancel the first term, then I'll get a 0. And if all of them add up in phase, I'll get a maximum output. Okay? So it's kind of interesting. This is a filter, but it has a filter with a very, very good physical intuition and physical meaning. There are the distance between these peaks in the optics world. This is a silly terminology, and I apologize, but you'll hear it if you go into optics, is the free spectral range. And it's an acknowledgement that the filter response repeats on itself every C over 2 and not L. Which, by the way, is also true for our Z-Transforms, right? Our filter response repeats all, at the sampling frequency. If you go back through and think about our sampling lecture, that's one of the things that we found. Okay? And then the sharpness of these bandpass filters, these resonance filters, is called the finesse. And a nice simple formula for that is that. And so this is the finesse, or it's the cavity, Q, the quality factor. And this is the sharpness of the peaks. Okay? All right. So that's an example of a filter, but let's tie it much more tightly to what we have been thinking about. If it's a block of glass, if it's an LTI filter, I should be able to model this as a signal flow diagram. I should be able to come up with all this stuff in the context of the Z-Transform, in the context of our filter approach. So the starting point for this, in my opinion, is to come up with a signal flow diagram for this. And so I'll have Vn, and I want to now consider this in the Z-Transform, not the sinusoids, but flip the sinusoids. And what happens is I'll have the first mirror, the first face of the glass, and I'll have reflected. And then I'll go through the delay. And then I'll go to the second face, the second mirror. And I'll have reflections back and the transmitted stuff. So this picture is sloppy. So let's be a little bit more careful about how we model the splitting of the first mirror, how we model the splitting of the second mirror, and how we institute our Z's for the delays. Okay? So Vn of Z there'll be a reflected wave, and then there'll be a transmitted wave through the first mirror. Part of that reflected wave is going to lead to a reflected output back at us. The stuff that goes into the material sees a delay block. I'll model my delay block in terms of my newfound friend, the Z-Transform, Z to the minus 1. And then I hit the second mirror, and some of it will leave and start to contribute to my transmitted voltage. Part of it will get reflected. And delayed as it comes back off that face. And then it'll see the mirror again. Part of that mirror will be reflected back. And part of it will be transmitted through. So this is the mirror block, this is the delay block, and this is the second mirror block, or the first face, the thickness of the glass, the second face. The impedance matching into the transmission line, the length of the transmission line, and the impedance matching out of the transmission line. Okay? Don't worry too much about that minus sign. That's only there to conserve energy. Okay? That's a little detail that you'll learn in EMAG. All right, so this is our signal flow diagram, and analyzing the signal flow diagram will allow us to immediately write down the transfer function. Okay, I'm going to do that. But first, let's take a look at it. It is something that this pops out at me, but it didn't earlier on, is this is a single input dual output structure. A single input double output structure. So one input actually gets split up into two outputs, the transmitted and the reflected wave. So that's kind of cool, right? Filters don't always have to be one input, one output. Filters can actually have multiple inputs and multiple outputs. And so all the scaling that we've done, all the things we've done, can scale up into multiple inputs, multiple outputs. This is a simple one. This is one input gets split up into two outputs. What goes through the glass and what comes back reflected at me. Okay? So that naturally came out of our analysis, and it's just remarkable to think about it a little bit, and then to think where it could go in the future, you know. And certainly MIMO, multi-input, multi-output signal processing, is huge. That's just a lot of applications for that. All right, now the way I like to model these, the way I like to analyze these, is I like to put in an intermediate variable somewhere like right around in there. So that's an internal signal. Okay? And then it becomes really easy to write down the equations of motion for this structure. Vt is equal to a of z, z to the minus 1, tr. Okay? So whatever this guy is, it gets delayed and sees this tr and gets shoved out as a v sub t. Okay? V reflected is equal to RL Vn of z. That's this guy right here. That's this path right here. Vn going into there, going out to Vr. And it's also equal to what comes up this branch here. That branch here is A times z to the minus 1 times R, whoops, delayed again, times TL. So this output here is this line plus this line. And I'm writing this in the kind of a funny way so that you see exactly where things are coming from. A times the first delay, times the reflected off of the right side, times another delay, times the transmit through the left mirror. Okay? And then my last equation is, what is A? Well, A is fed by Vn. So that's Vn of z times t left. And then it's also equal to what A was before, having gone around this loop. So this is equal to minus A of z, z to the minus 1, RR, z to the minus 1, RL. And the minus sign comes in from the sign on the RL. Okay, so that's this set of equations. Here's an output, and here's the input. Okay? So the outputs and the inputs. And what we don't really care about is that internal signal. So if we eliminate that, and this is just simple algebra. For now it's simple algebra. Oh, there we go. Sheesh. So there's what A is. So now if I substitute into the other two equations, I get V transmitted of Z is equal to V input of Z times TR, TL, Z to the minus 1 over 1 plus RL, RR, Z to the minus 2. And I have the reflected and that's right, but it's a little bit ugly. It's actually a parallel form, right? It's actually a parallel form. We can recognize that. And I can rearrange this to our direct form in terms of polynomials. And remember, we want, for a stable device, we want the denominator to be within the unit circle. So we call that our region of convergence. So the magnitude of Z must be greater than that, or that must be less than 1. Okay? So we can take the same structure and we can model it. The physics people tend to model this structure this way, summing up all the components of the delayed. But engineers tend to look at it this way. And so instead of doing that infinite sum, they turn things into an algebra equation. Okay? This is very much more powerful. This is very powerful because this approach scales. What if I have 2 blocks of glass? What if I have multiple transmission lines? What if I have transmission lines that tee off to feed whole nother circuit, or 2 different antennas? So if I have a whole nest of these feeds, if I have a whole nest of these waveguides, if I have a whole nest of these mirrors stacked up on top of each other, how do I scale that? Well, the summation isn't going to cut it. But this is going to be, I can continue to add all kinds of structures directly to it. So this picture here it's such a small little connection, but moving from the infinite sum and the classical analysis to a picture like this changes everything. It allows you to do design. It allows you to scale. It allows you to make much more sophisticated devices. And just to give you a little bit of a history, this actually comes out of my own research back 20 years ago. Okay, there was something about the realization that a block of glass was that linear time-invariant element, that it really did filter, that led me to say, I've got to come up with a signal flow diagram for this. I was working on a problem that needed the analysis, and it was getting intractable. And so I thought, I took a day, and I carefully thought through this structure like this. And a friend of mine who's an expert in signal processing, he collaborated with me, and we ended up analyzing this and bringing this whole Z-Transform business into the photonics world, into the optics world, and the electromagnetics world. Before that, people hadn't really made this connection, and so we were the first people that did. When I worked in the fiber business, when I worked in the optical communications, I'd go up to say JDS Uniphase, which was a huge provider of filters and components and everything. And by the time 2000 rolled around, sort of published these papers in 94, 95, 96. By the time 2000 rolled around, most of the engineers were sitting in front of MATLAB designing their filters based on these structures, on this approach. Okay? It wasn't that it came up with anything new, just made that connection. But by making that connection, it unlocked all the power of all the algorithms, of all the digital signal processing that flooded back into photonics. And that hasn't stopped today. So your fiber optic systems are this perspective is modern and very, 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 very powerful. Okay. Let's see. Once you have these transfer functions, you can write the difference equations for them, so you can see these in terms of difference equations. We've probably done enough of that we don't really have to go too much more into that. You can write these in this is a parallel form, but you can also write them in cascade form as well. The interesting thing about that is it has the same transfer function, but it's not the same device, right? So it's not. We started by looking at the reflections in a transmission line, the reflections through a block of glass, and when you rewrite it, it's no longer that. It's something. It's a completely different architecture for waveguides and all, but it leads to exactly the same result. So there's something kind of cool about that I don't have a lot of philosophy on just yet, but it's kind of there. All right, we have about 7 minutes. Do you want me just to go through the highlights of the course, or do you want to quit? Highlights? You have 40 or so folks at home waiting your decision. All right, let's see. I'm just going to show you my notes for these. I think you can read those. I'll just walk you through them. Okay? So here's the review of the course as I see it. And I'm purposefully not adding in all the math. I'm just sort of guiding you into the big picture of things. So if you go back through your notes, if you go back through the text, you'll see these as the highlights. And then you'll see some specific mathematics. And then you'll see example after example after example after example. Okay? So I've stripped away all the examples, and I've minimized the mathematics so you can see just how much money you wasted on such few amounts of information. That's supposed to make you feel good going into studying for the cumulative comprehensive exam. I know, I have a very warped sense of humor. Chapter 1 was all about math, signals and systems. Continuous time, discrete time. Okay? Derivatives, differences, integrals, sums. A lot of what we do comes back to those pairings, right? And the fact that differences and sums belong in discrete time, Z-transforms and things of that nature. Continuous times are derivatives and integrals. And there's going back and forth now should be second nature to you. Okay? Low pass and high pass as well. Starts to rear its head in there as well. Energy and power. Okay? Transformations of signals. How do we get more out of a sine wave? How do we get more out of a delta function? How do we get more out of a step function? So we can scale the scaling in time, shifting in time. Those are two main manipulations, transformations. The scaling in time, if a is equal to -1, brings up this issue of parity, odd functions and even functions. Okay, so there's a lot of discussion about odd and even, parity, taking an arbitrary signal and breaking it up into its even part and its odd part, right? So all that stuff is floating, is mathematics that's floating underneath this one particular little avenue. If the function repeats itself, then after a certain magic T naught, then we have periodicity, periodic functions. And that was a whole other set of very interesting digressions that led to on and off all over the semester of what happens when things are periodic versus aperiodic. Okay? So these simple transformations in Chapter 1 unlocked a lot of things in Chapter 1, 2, 3, and so on. Okay? Delta functions was, I think it's fair to say this is your first real introduction to this magical function, this sharp impulse. And the most important thing to remember is the sifting property about that, because that saves your headaches. You know, what it does is it allows you to do those integrals. And frankly speaking, as we saw last class, on Wednesday night, there was a convolution integral that we easily did because of the sifting property, right? And as soon as we said that we saw it was going to be a convolution, everyone tensed up, and then when we saw that it was a delta function and sifting, everyone the whole class just relaxed, right? I felt it. I don't know if you guys felt it. It's magical. Systems and properties of systems: memory, invertible, causal, stability, time invariance, linearity. Most we looked at linear time invariant systems in the course. But even, we talked about causality today, right? We talked about stability today, where pole placement. So again, these themes resonate. Memory, by the way, is another when you think in terms of FIR and IIR, those also talk about memory, right? So those are themes that have gone through the entire course as well. Chapter 2, linear time invariant systems. Delta function responses lead to transfer functions, h of t and h of n. From there, we get, because it's linear time invariant, superposition, time shifting, holds, convolution sums, convolution integrals. If you think back, if you look through your notes, you will see example after example after example after example of convolutions. But in a heartbeat, it's just those equations, right? So again, very, very small number of topics with a lot of beef behind it. Properties of convolutions: commutative, distributive, associative. And then even today, we were looking at block diagram representations of different differential equations, difference equations, signal flow diagrams, and so on. Okay? Fourier series. A huge philosophical discussion on orthogonality. What it means. That concept is just very, very, very important. And by the way, it holds for sines and cosines. And by the way, that's the way we're able to come up with Fourier series and actually evaluate the coefficients of Fourier series. So the role of what is orthogonality and its role in Fourier series for continuous time signals: trig, exponential, Fourier series, again, doesn't matter. You should use what's easier. I want to remind you of Parseval's relation and convergence in the mean. That was a particularly sticky derivation, but also one that's very, very useful and very, very important and very fundamental. So that day's notes you might want to go back and look at. And then Fourier series for discrete time signals, we did a little bit of that as well. Okay? Chapter 4, this is really the last page. Continuous time Fourier transforms. Fourier transform pairs. Okay, the whole concept of moving back and forth between time and frequency. Properties of those Fourier transforms: linearity, time shifting, conjugate and conjugate symmetry. That was a hard derivation, but go back over that and take a look at that as well. Differentiation integration, that leads to our high-pass filters and low-pass filters. Critical, absolutely crucial in terms of your intuition and your understanding of what is a differentiator versus a low-pass filter, high-pass filter. What is an integration versus a low-pass filter? Being able to make that connections mathematically, which we did, and also intuitively, really is a very, very powerful thing that you guys should talk about it and become comfortable with in this course and in others as well. Time and frequency scaling, duality, going back and forth. Parseval's relation, that's a nice one. Convolution and modulation property. So the convolution property led to filters, which I think is covered in Chapter 6. So I did a little bit of Chapter 6 buried in with convolution properties. Modulation property, that's going to be big in comm systems, and big in instrumentation and big everywhere else. So these two guys are very, they're related. And then we also did a lecture on sampling, the sampling theorem. Again, absolutely critical to a modern electrical engineer. And then today's lectures were about the Z-Transforms. Okay? So really not much. Especially if you strip away all the examples. Right? I spent a lot of time on examples, which I think is the right way to teach the course. But now as you study, you should take a picture like this like these, these 4 pages that I just went really quickly through, and that becomes your backbone.